Alright, so this is going to be the part 4 of the series of videos that we are making on the problem of this inclined disc rolling without slipping inside a hollow cylinder, and this is going to be the last part. This is going to be a rather short video where we will point out a couple of interesting observations that can be made about the overall motion of this inclined disc. Just to recap, the problem goes as follows. As you can see in this figure, there is a disc that is mounted on a rod. The rod is bent. You can see that the rod is forming the vertical axis of a hollow cylinder, but at the point B the rod is bent, and the bent part of the rod is of length L. It is shown here. So the bent part of the rod is of length L, and at the end of the rod there is a disc of radius R, and the disc is such that as this rod turns about the axis of the hollow cylinder, the disc rolls without slipping on the inside of this hollow cylinder. Now it is given that the vertical portion of the rod turns with a constant angular velocity of capital omega. It is shown in another figure over here, where the variables and coordinates are written a little bit larger font, and the incline at which the rod is bent is given by the angle beta, and the question that is asked is that, given this kinematic setup where the disc is rolling without slipping on the inside of the cylinder due to the bent rod, what is going to be the angular velocity of this disc? What is going to be the angular acceleration of this disc? And furthermore, it is asked what is the acceleration of the point C. Now the point C is shown over here, or you can see it over here. This is the instantaneous contact point of the disc on the inside of the hollow cylinder. Clearly the point C is going to have a zero velocity, but the question asks for the acceleration of the point C. So in the past 3 videos, or rather I should say in part 1, part 2 and part 3 of this problem, we have solved and answered these questions by using different rotating frames and different rotating triads. And in particular, we have emphasized on the distinction between the rotating frames, the rotating reference frames, and the triads. We have shown how to treat them separately. We have emphasized that the triad is simply the setup that is used to indicate the unit vectors. The rotating reference frame, on the other hand, is, as the name suggests, a frame of reference, and it is a frame of reference that we as the problem solver need to put us in when we are visualizing these vectors, when we are formulating these vectors. With that understanding, we have essentially what is happening is, let me just go over this figure. This is a schematic of what is going on with the disc. You see the point B is the point where the rod gets bent. The rod is turning with a constant angular velocity of capital omega. The bent part is making an angle beta. The point C is instantaneously the point of contact of the disc with the inner part of the cylinder. Phi dot is the spinning angular velocity, and we determine this velocity by imposing the rolling constraint as part of this problem. The default triad that has been used to solve this problem is a triad X, Y, Z, where X where Z is along the bent part of the rod, so it is essentially forming the axis of the disc. X is parallel to the surface of the disc, and Y is going to be pointed inside the surface of this page, or rather pointed outside the surface of this page, and XY forms the plane of the disc. It forms a plane that is parallel to the disc at a distance of L from the disc itself. One can also see that at any given instant, Y is going to be horizontal, and furthermore XZ, the plane XZ, forms a vertical plane, and that vertical plane cuts through the vertical axis of this bar, or the vertical axis of the axis of symmetry of the cylinder. Now the results, there are two particular results that we would like to take a look at. The first result is the angular velocity of the disc. So let me just the net angular velocity of the disc is given by this expression. So let me just write it down so that everything is in our view. I have represented the net angular velocity of the disc by omega d, and so omega d is given by, let me check the expression, it's capital Omega sine beta times r. So r capital Omega sine beta times Lk plus capital Ri. So Lk plus capital Ri. So that's the angular velocity of the disc, and so this angular velocity of interest in the observations that we are going to make. And the other vector that is of interest is the acceleration of the point C, and the acceleration of the point C, that is this point of contact, is given by the following expression. Let me just, it is given by capital Omega squared sine beta times cosine beta plus L over R sine beta, and beta is of course an acute angle, RK minus LI. Okay, so with that we do have the two vectors that are of interest in the observations that we are going to make about this problem. So, all right. So now if we consider let's consider the vector going from B towards C. So rho, which is going to be rho C with respect to B. So the vector rho C with respect to B is the vector going from B towards C, and based on this triad that we are using to represent all these vectors, that vector is given by Lk plus Ri. Okay, so that's the vector of C with respect to B. Now you can right away see from the expression of this vector, if you compare it with the expression for omega d, one thing that we notice is that these two vectors are parallel. Okay, so we notice that omega d is parallel to rho C with respect to B. So this is, or rather we can say that because these two are in the same direction, the cross product is equal to 0. Therefore omega d parallel to rho c with respect to b. Right, so these two vectors are parallel, so their cross product is 0. Another observation that we can make is the following. It is that if you consider this acceleration, then this is just a scalar term or multiplier term. This is actually defining the direction of this vector. You'll see that the dot product of these two vectors, the dot product of the acceleration with rho c with respect to b, is equal to 0. So also rho c with respect to b dot ac is equal to 0. Therefore rho c with respect to b is perpendicular to AC. So here we have a very interesting observation that the angular velocity of the disk is parallel to CB, and the acceleration of the point C is perpendicular to CB. So this is the classic case when a rigid body is rolling without slipping on another surface. Okay, in this case we can imagine the following to be happening. Let me just let's say this is our point B, and we draw a vertical line from point B. Let's say this is our point C, right? And the angular velocity of the disk, so the disk is over here. You see the disk is over here because the bent bar goes like this. Okay, so the disk is like that. All right, now the angular velocity of this disk is parallel to the line BC, and we can extend it. What does that signify? Well, it signifies as if there is a cone okay, that at this instance is rolling without slipping on this axis. So it is rotating about this axis, because if your rigid body is rolling without slipping on another surface, at any instant it is spinning about the line of contact. So it's almost like this is the instantaneous line of contact, and this cone, which is formed by the disk with CB on one side and this line which joins B with the diametrical opposite corner of C, or opposite point of C. This is A, by the way. Then we see that the cone is completely turning about this line. Okay, and that is a classic case of rolling without slipping. Further proof of the fact that this is indeed representing rolling without slipping with BC as the instantaneous axis comes from the fact that the acceleration of the point C is perpendicular to BC. So the acceleration of point C is perpendicular to BC. It's not along CA. Keep that in mind. It is perpendicular to BC, and that is also it can be verified. For example, if you work out the acceleration of the point of contact of a cone on a horizontal surface, you will be able to show that the acceleration of the point of contact, this point of contact, that is the end point of the cone at the flat surface, that acceleration is perpendicular to the instantaneous line of contact. Here this is the instantaneous line of contact. So these two together basically confirm that indeed the cone at this instant is rotating about the line BC, and as the cone practically physically goes and rolls without slipping on the inner surface of the cylinder, what will happen is that it will trace that contact point will essentially trace a circle. Now that circle forms on the inner surface of the cylinder, however, if we look at that circle with respect to the point B, then it's a cone. Okay, so if we consider all the points of contacts that form on the inner surface of the cylinder as the disc rolls without slipping, then what we get is a cone. Okay, and that cone is referred to as the space cone, because it is not really a physical cone, it is a conceptual cone that is being formed with respect to that point B by joining the point B with all the points of contact on the inner surface of the cylinder. Okay, that's how we get the space cone. On the other hand, if we take the disc and if we consider a hypothetical extension from point C to B and C prime to B, and then we form a cone, that cone is referred to as a body cone. And this cone is more physical because instead of the disc, the idea is instead of the disc, if you had a cone like this, the motion would be exactly the same. Okay, so this is a body cone, and it's also called the body cone because it contains the instantaneous points of contact, or instantaneous points of contact, yes, on the actual body of the disc. So you see C, C prime, C double prime, or you can call them C, C1, C2, C3, etc. They are all points on this, on their physical points on this cone. And because they are physical points on this cone, it's called a body cone. Whereas the same point of contact, when you consider on the cylinder, then C, C1, C2, etc. will form points on the cylinder, but it's not going to form a point on the object that itself is turning, and you create a hypothetical cone if you join those points to the point B, and that is called the space cone. And so in this case, what is happening is that the body cone is rolling without slipping inside the space cone. And so this is the observation that we make, and it's interesting that similar interpretations of rigid body motions can be made when a rigid body has free rotations in space, which leads to the idea of precession of rigid bodies. If you look at the rigid body's motion from a certain direction, you see a regular precession happening in rigid bodies that are rotating in space. And there again, you can interpret the motion of the rigid body in the form of a body cone and a space cone. So it is interesting that this idea of body and space cone, they come up over here, and I wanted to bring this up in context of this problem. As we solve different problems on the techniques of dynamic analysis for rigid bodies, this idea of body and space cone is going to come up more often, and hence it has a relevance when it comes to rigid body motion. So that is it. That's all I had for this video. Again, it's a short video, just finishing our discussion on this disk rolling inside a hollow cylinder problem. This problem has allowed us to do the analysis in various ways. It has allowed us to look into different aspects of rotating reference frames and make a contrast with the rotating triads. So it's a pretty rich problem when it comes to the different features that this problem provides. Thank you so much.